Okay, in this video we're going to be talking about experiment 10 where we're making copper 2 plus solutions and examining them by spectroscopy. So what we're doing is we're thinking about a real life application of some of the knowledge we got in chapter 7 where we were thinking about different wavelengths of light and energy, and now we're applying that in what's called a new instrument that we haven't used before. It's called a spectrophotometer. So spectro refers to the spectrum of light, photo meaning light, and the meter is measuring it. And so this instrument is incredibly useful for a variety of reasons, and you actually end up using it a lot in Chem 104. And the reason why it's useful is it measures the amount of light a sample absorbs based on the concentration. So in this experiment, we're also using our knowledge from chapter 4 where we're thinking about concentrations of samples, molarities, dilution, solution making, all of that. When we are using a spectrophotometer, before we use it, we have to select the proper wavelength to ensure that the sample is absorbing as efficiently as possible. Because if you choose the wrong wavelength, then your sample doesn't absorb as much light as it should, and it makes it harder to understand the data that you're collecting. So qualitatively, what we can do when we're thinking about what the best wavelength is to set our instrument to so it collects our absorbance correctly, we can use the color wheel. So in this particular experiment, we're looking at copper 2 plus, specifically CuEn2 2 plus samples, and these samples are violet, so that's the color we see. That means its complementary color, the one directly across from it on the color wheel, is the color of light that is being absorbed. So yellow light is being absorbed, violet light is what we see. So what happens in this instrument is that light hits our sample, and then some of that light is absorbed. So the fraction of light that is absorbed is the reading that we get from our instrument, and that is called the absorbance. And because it's a fraction, this value has no units. So we're just going to get values that are less than 1. They are fractions. They have no units. Okay? So when we're thinking about all of this, it's helpful to go to the first page of our data sheet and think about this and how we're setting up our instrument. So let's go to the first data sheet for this experiment. It's on page 86. And we're going to start by using the color wheel to predict what color light we expect our solution to absorb. So this is essentially what we just did above on the pre-lab sheet. And again, we know that we are seeing the violet light, so the sample has to absorb yellow light in order for us to see violet. So what color light would we expect our solution to absorb? We expect the solution to absorb the yellow light because it's the complementary color of our sample color. Of the color of our sample. So that's a qualitative approach. So we expect it to be somewhere in this yellow range. Now what we're going to do is use a quantitative approach. So what we did was we collected absorbance values. So notice all of these different fractions that we collected based on different wavelengths of light. So we could plot this information. And this is something you see a lot of the time. You might see it on a quiz. So wavelength in nanometers versus absorbance. So this type of plot pretty much always looks something like this. There's going to be a maximum absorbance, or a maximum wavelength where we have, there's going to be a wavelength at which we have a maximum absorbance, and that is known as the lambda max, okay? So this is a wavelength, as you learned in Chapter 7, where we have the highest possible absorbance. If you look at this table, table 10.1, you'll see that the value for the wavelength at which we have the highest absorbance is 550 nanometers. So that is our lambda max. 550 nanometers, right, if we look at our color wheel, is in this yellow range. And so that makes a lot of sense. So both quantitatively and qualitatively, we can assign what absorbance value we should have for this particular solution. So our solution is violet. The color of light we would expect to absorb the most is yellow, and in fact that's what we see. And so this is going to be the lambda max value, or the wavelength value that we set our spectrophotometer to, so it reads our sample efficiently. Now going back to our pre-lab sheet, we see that one of the first parts of this experiment requires us to make a solution of our CuEn2 plus sample. So the first thing we're going to do is make the sample by adding copper 2 sulfate to ethylene diamine. And we're doing it in a 50 milliliter flask. So our first job is to figure out the molarity of this solution. So we've got 0.129 grams of copper sulfate pentahydrate. And we know that anytime we're finding a concentration, we need to use the molar mass. So 1 mole of copper sulfate pentahydrate has a mass of 249.685 grams. And based on the equation in your manual, you'll know that you have 1 mole of copper En2 2+. This is also often referred to as copper 2+ in your experiment, for every mole of copper sulfate pentahydrate. And so now that we have the moles of our solute, we can divide it by the volume, so 50 milliliters. And of course, we always change our concentration, or our volume, to liters when we're calculating a molarity. And we get 0.0103 molar CuEn2 2+ solution. So depending on what mass you weigh out, that will change your concentration somewhat, but the overall process for doing this calculation will be the same. The next thing we do in this experiment is we take this stock solution here and we dilute it with water. So anytime you see the word dilution, you use the dilution equation, which says that C1V1 equals C2V2. So let's do an example calculation. Let's say that I used a burette to measure out 2.05 milliliters of my stock solution into a 25 milliliter flask, and I filled to the line with water. So I want to know the new concentration after I perform this dilution. The original concentration is 0.0100 molar. This will be whatever you calculated, so your value. The V1 here is 2.05 mils. Yours will be somewhere close to that as well, but again, use your value. If you happen to have 2.05, that's great. If not, that's fine. Just use whatever you got. The new concentration is what we're looking for, and the new volume is 25 milliliters because we're preparing it in a 25 milliliter volumetric flask. When we do the math here, we find that the new concentration is 8.20 times 10 to the minus 4 molar. So this will go in our data sheet. Once we have done this for all 4 solutions, so you're going to be prepping 4 solutions and calculating their concentration by doing this same calculation, we are going to make a Beer's law plot. So Beer's law relates the absorbance with the concentration using a couple of constants. So when we're thinking about epsilon B, epsilon is really just a constant that relates absorbance and concentration, but it's for a particular substance. So this value changes depending on the identity of the substance. Okay. B is the path length, and this value is pretty much the size of the container that you put your solution in. It's pretty much always 1 centimeter, so that we don't have to worry about it when we're thinking about our solution making in our calculations. And C is the concentration, and it has units of molarity. So this is concentration. And this lines up with a trend line from the equation. So if you plot absorbance versus concentration, you will get a trend line, which is y equals mx plus b. Ideally, b will be 0, because if you don't have any solute in your sample, it shouldn't absorb any light, because the absorbance is only measured for samples that have some color to them. Okay, this value probably won't be 0 in your experiment, but for you it should be somewhere close to 0. Okay. Once we have this trend line, if we know the absorbance of our solution for a random sample, then we can calculate its concentration. So using the plot here, we want to know the concentration of a sample that has an absorbance of 0.653. So in this particular plot, I have an equation which is y equals 196x. You will have a different slope and a different intercept than I have here, so just use the data you have. Don't be alarmed if yours is different. This is just an example. And I'm going to plug in the absorbance for my y value. So 0.653 equals 196x plus 0. I can subtract 0 from both sides, which does nothing, then divide by 196. And I get that the concentration of this sample is 3.33 times 10 to the minus 3 molar. So if we look at our data sheet, we can see that this exactly follows with what we did above. So you're going to prepare your stock solution. You're going to show your work in this box below. The ethylene diamine will not change this volume. The role of the ethylene diamine is just to create that bright violet color that we're looking for, because otherwise this copper solution is just blue. Then in part B, we're doing all of our dilutions. And so this is where we use our dilutions. And you're going to show your work for solution 1 only. Just for solution 1. And this A is the absorbance values that you're going to be recording from the instrument. Then, once you're finished collecting your data, you're going to make a plot of these values and put your trend line here in this box. Then you will find the unknown, it will be given to you, and you're going to record its absorbance in this box. And then you're going to use the trend line to solve for the concentration just like I did above. Okay, and you're going to do it in that box. We will not be doing this part, so you can cross that off on your data sheet. And the rest is really shown for you. You can put all of this information into your Excel plot so that it's available to you. So that is experiment 10.